Hi everyone, we're taking a look today at something called 77 in class max min worksheet. It's been a while since you thought about maximums and minimums, and I thought maybe we should go back and take a look at some of those before you took the test. For each of the following functions, find the values. What is the max? Not where is the max of the absolute max and absolute min on the given closed interval. Okay, so in number one, we're given a parabola. We're told that y equals x squared minus 2x minus 8 on the interval from 0 to 4. Okay, so when I think about finding mins and maxes, I always think about setting the derivative equal to 0, finding when the derivative is undefined, and checking the endpoints of a bounded interval. Okay, so let's do that. We have y prime equals 2x minus 2. If we set y prime equal to 0, we get x equals 1 as a critical number. This derivative is a linear function, and a linear function is never undefined, so I don't have to worry about that. But I do have these two endpoints to consider. So I've got 0, 4, and my critical number 1. All right, so let's think what we've got going on here. If we plug a 2 into, remember, this is a y prime sign chart. If I plug a 2 in here, I'm going to have 4 minus 2, which is positive. And if I plug a 1/2 in here, 2 times 1/2 is 1 minus 2 is negative. So I see I have a minimum here at x equals 1. Now, what about this? Well, from x equals 0 on, y prime is negative, which means y is decreasing. So I've got this point, and then y is decreasing. So that's a max. And I'm increasing on y until I get to 4. Increasing until I get to 4. Now, I don't know how I'm increasing necessarily. I just know I'm going up, and therefore that 4 is going to be higher than over here at 1. So this is also a max. But I was told to find the absolute max. And while I know I have the absolute min, because it's the only min, what about the absolute max? Well, I'm going to have to evaluate the function at each of these points, y of 0 and y of 4. So if I plug a 0 in, I get negative 8. Well, it's kind of small for a max. And if I plug a 4 in, remember, these are going into y, not y prime. I want to know the value of the function at each of these points. So if I plug in a 4, I've got 16 minus 8 minus 8, which is going to be 0. So, yeah, 0 is actually bigger than negative 8. And were we supposed to find? Yes, we were supposed to find the value at 1 as well. So if I plug in 1 for y, I'm going to have 1 minus 2 minus 8, or negative 9. Yep, that's the min. And this is the absolute max. Don't forget, you have to write your justification sentences for these. So, the absolute min occurs at x equals 1. It is the only min. And I know it's a min because to the left of x equals 1, y prime is less than 0, and to the right of x equals 1, y prime is greater than 0. And you know, there's an absolute min of negative 9. Yeah, I'd like to get that into the sentence as well. And my maxes, well, I'm going to say there are 2 maxes, one at each endpoint, but the absolute max occurs at x equals 0. Was it 0? No, 4. With a value of 0. I do want to write a justification for that, but yeah, okay, I'll write the justification. X equals 4 is a max because to the left of x equals 4, y prime is greater than 0, and x equals 4 is the right endpoint. Okay, so that's one. Let's go down here and take a look at 2. 2 is another parabola. So we've got y equals 4 minus 4x minus x squared, and we're on negative 1 to 4. So then y prime is negative 4 minus 2x. And if I set y prime equal to 0, I get 2x equals negative 4, and x equals negative 2. Okay, and uh-oh. What does that mean? It means I don't have any critical points on that interval. But I am going to go back and check my math. And in fact, I'm going to go all the way back to make sure I didn't copy the problem down wrong. Minus 4x minus x squared. Take the derivative, set equal to 0, add 2x to both sides, divide by 2. Yeah? So at x equals negative 2, I'm supposed to have something, but that's outside this boundary. So, yeah, no, not going to work. Again, this derivative is linear. Linear functions are never undefined, so I don't have to worry about that. All I have to do is check my endpoints. So if I plug in a 4 here, I'm going to have 16. I'm going to have 16. I'm going to have 4. 4 minus 32 is negative 28. Y of 4 equals negative 28. And if I plug in negative 1, it's going to be positive 1. Oh, but I'm subtracting it. That's going to be positive 4, because minus a minus 1. So I have 8 minus 1 is 7. So y of negative 1 equals 7. It looks like I have my absolute max here and my absolute min here. So let's put these off to the side. Negative 1 equals 7. So we can say the absolute max of 7 occurs at x equals negative 1. To the right of x equals negative 1. Y prime is, I never changed. Negative 1 to 4 in y prime. And if I plug in a 0 for that function, I end up with positive. But that's not what's happening here. Oh, I plugged that into not the derivative. Minus 4 minus 2x. Now I plug in the 0 and I get negative 4. So this function is always decreasing. Y prime to the right of x equals negative 1. Y prime is less than 0. And x equals negative 1 is the left endpoint. Since this is the old max, it must also be the absolute max. Okay, and remember, they asked us here for the value of the maximum, so it's terribly, terribly important to say what the value of the maximum is here. If I just say when it occurs, I'm going to lose the answer point, no matter how many beautiful sentence things I make over here. As far as the min at 4, we can just change the sentence a little bit. And that's 4 to the left of 4 to the left of 4, y prime does, and x equals 4 is the right endpoint. This should say min, and this should say min. Okie doke, there's number 2. How about number 3? 3. Y equals 3x minus x squared, and negative 2 to root 2. Alright, so y prime is going to be 3 minus 2x. Again, I have a linear derivative. That's never undefined, but the linear derivative is equal to 0 at x equals 3 halves. And is 3 halves on this? Well, I think so. I know the square root of 2 is approximately 1.41. And if I multiply that by 2, I've got 2.82. Well, this is 1.5, and that's in between negative 2 and 2.82. So I think this point goes on our number line. There's negative 2, there's 2 root 2, and there's 3 halves. If I test 0 in the derivative, I get a positive, and a number between 1.5 and 2.8, well, I'm going to go with 2. Then if I plug a 2 in here, 2 times 2 is 4, 3 minus 4 is negative 1, so that's a minus. So it looks like I have a max here at 3 halves. What's the value of that max? Well, you know what I'm going to do? I'm going to use synthetic. Negative 1, 3, 0. Negative 1, negative 3 halves, 3 halves, 9 fourths, 9 fourths. Okay, so I get a value of 9 fourths. You're, of course, welcome to plug the 3 halves in for all of the x's to find what the value of the function is here at 3 halves. And I'm going to say y of 3 halves equals 9 fourths, and we say that's max. If I plug a negative 2, because I've got these 2 minimums here to consider, if I plug in a 2, I get 6 minus 4, which is 2. Okay, so y of negative 2 equals 2. That's a min. Well, that's, 2 1/4. That's 2, so that is lower than that. And then finally 2 root 2. So what's that going to look like when I plug that in? I'm going to have 6 root 2 minus 2 root 2 squared. 2 squared is 4, root 2 squared is 2, 2 times 4 is 8, 6 root 2 minus 8. What an interesting value. So just to be sure, this says 6 root 2 minus 8, and I get 0.485. Okay, well, 0.485 is lower than that minimum. How can that happen? Because it's on the other side. Oh, yeah. Yeah, I definitely agree with that. So, y of 2 root 2 is going to be 6 root 2 minus 8. Okay. This minimum here is higher than the 0.485 minimum here. So this is my absolute minimum, and there's my absolute max. I'm going to not write the justification sentences, not because I don't love you, but instead because I'm tired of writing them. All right, I know that one's a little capricious, but no, I have to get this done expeditiously, and I know you can find the write-ups in oh, look, answers on the bottom. -10. We didn't get -10. What's up with that? Huh, we did get this one. Did we get that one? All right, I'm going to have to check these answers. You hopefully, if there's something that needs changing, I will have changed it before you do this. Okay, and so the last one, number 4 for this section, y equals x minus 4 to the 5th on 3 to 6. All right, well, I mean, let's think about this for a second. This is x to the 5th shifted right 4. So we know that's where the vertex is. That looks a lot like a min to me, but we're going from 3 to 6. Well, you know, that's a max. That's a max. That's my only min. And I can see here at 6, I'm higher up than I am here at 3. So I have an expectation that the absolute max will be at 6 and the absolute min will be at 4. But let's see. Y prime equals 5, x minus 4 to the 4th times 1. Okay, so if I set y prime equal to 0, 5, x minus 4 to the 4th, and then I divide both sides by 5, I get 0 equals x minus 4 to the 4th. And when I take the 4th root of both sides, I get x minus 4 equals, yes, it was an even root, so yes, I should do plus and minus, but plus and minus 0 is still 0. And so I get that critical number of x equals 4. 4. We've got 3, we've got 6, and we've got a reminder that this is y prime. Okay, so if I plug in a 5 here, 5 minus 4 is 1. 1 times 5 is 5. That's positive. And if I plug in 3 and 3.5 here, 3.5 minus 4 is -1/2. But -1/2 squared raised to the 4th is going to be, -1/2 to the 4th is -1/2 times -1/2 times -1/2. Well, this is a little surprising to me because I'm sort of expecting to get 0 here. When we looked at this graph, didn't we have a horizontal tangent here at 4? So shouldn't my derivative be, oh, my derivative is 0 at 4, and oh, there it is. So what was this? Oh, this was testing. So I expect negative between 3 and 4. I don't seem to be getting negative here. So what's happening? 3.5. 3.5 minus 4. Oh, it's to the 5th. No, I'm putting it in here because I want to see if I'm positive or negative. Huh. That's very interesting. Because negative times negative times negative times negative is definitely going to be a positive. I'm going to have 1/16 there, not. I'm going to have positive 1/16. I don't get that. What am I missing? 5 times 5/16, but negative to an even power. No. What am I missing? Let's try to graph it. X minus 4 raised to the 5th. And we want to look from 3 to 6. Go -1. Let's see what happens. Look, Mr. Kukla truly is sleepy. The original function is not the parabola shape. The original function is a fifth-degree polynomial. A fifth-degree polynomial that has a zero slope at 4, but neither a min nor a max, and keeps increasing. So what I'm seeing here is what I'm supposed to see here, and I really love that about math and being awake, right? Like, I had this full expectation that I was thinking about this shape, but this is the derivative. That's the original function. And I was basing my assumption about what the SIGN should be over here based on thinking about the graph of this. And really, I was supposed to be thinking about the graph of this fifth-degree polynomial, which is increasing until 4, where I have a slope of 0, and then after 4 is increasing again. So in this situation, my minimum is at 3, and my maximum is at 6. Okay, so if I plug in 3, 3 minus 4 is negative 1. Negative 1 to the fifth is negative 1. So y of 3 equals negative 1. And what about y of 6? Well, 6 minus 4 is 2. 2 to the fifth is 32. And so here's my absolute max of 32 at x equals 6. And my absolute min at x equals 3, my absolute min of negative 1. Okay, and don't forget to write the justifications for those. Problem number 5. A rectangular field bounded with a fence on 3 sides and a straight stream on the 4th side. Ooh, look at the stream. Okay, so we've got width, we've got length. Find the dimensions, maximum area that can be enclosed with 1,000 feet of fencing. Well, that fencing has to cover this and this, 2 W's plus the straightaway L. And I know the formula for area here is length times width. Remember, we're supposed to try and identify the thing that has the superlative. What are we looking for? Oh, maximum area. So I don't want to take the derivative of this. I want to take the derivative of this. Furthermore, I think it's very, I don't usually take the derivative of the thing that has a number equal to. That's pretty much the domain of my helping equation. But over here, I'm going to want to take the derivative, but I really want to take the derivative in terms of only one variable, not these two. So I'm going to come over here to my helping equation, and I'm going to say that 1,000 minus 2w equals L. Therefore, where I see L over here, I can replace L with 1,000 minus 2w. So I'm going to have 1,000 minus 2w times w. And sure, I think distributing here is great, but check it out. We actually know where the intercepts are here. One of them is at 0, and the other one is at 500. And we know this is a down-pointing parabola because we get negative 2w squared. And so we're looking at something like this, where the maximum must be here, halfway in between. So we can do a lot of thinking about this, but let's show some calculus. That's what the AP readers are going to want to see. So A of w equals negative 2w squared plus 1,000w. A prime is going to be negative 4w plus 1,000. And if I set, this is never undefined. If I set A prime equal to 0, I do get that w equals 250. Okay, so if I put something in A prime over here, I don't know, like 1. 1,000 minus 2, 998, times 1 is still 998. But if I come over here and plug in a number like, I don't know, how about 1,000? 2 times 1,000, well, it's 2,000. 1,000 minus 2,000, that's negative. Times a positive 1,000, that's still negative. So I've got negative over here. It looks to me like I've got my absolute max occurring at 250. And does it say find the dimensions of the field with the maximum area? It wants the dimensions. It does not care about what the maximum area actually is. So if W equals 250 is my maximum area occurring, then I want to take this W, plug back in here. So 1,000 minus 2 times 250 is going to be my length, or 1,000 minus 500, not 5,000, equals the length. So 500 equals the length. So I'm going to write some sort of justification sentence now that says the max area is found with a rectangle whose dimensions are 500 by 250, because to the left of x W equals 250, a prime is greater than 0, and to the right of W equals 250, a prime is less than 0. Okie doke. All right, let's take a look at number 6. Number 6, find the lengths of the sides of an isosceles triangle whose perimeter of 12. And we're looking to maximize area. So if I think about an isosceles triangle, and it says isosceles, it doesn't say isosceles right triangle. So that one's equal to that one. X, X, and Y. Okay, so we know that the perimeter is 2x plus y, and we're told that the perimeter is 12. Sure looks like a helping equation to me. Now, what about the area here? I feel a little uncomfortable about that. It's an isosceles triangle, but it's not a right triangle necessarily, right? I mean, these don't have to be 90s anywhere. And, you know, if this were a 30, 60, 90 right triangle here, well, I could use my triangle properties, but yeah, I don't have that either here. That's very interesting. I kind of want to see what was I thinking. My suspicion is going to be that area is maximized when all of these sides are equal. So, well, oh wait. So I know that this is equal to this from that isosceles triangle theorem, where if these sides are the same, then the angles opposite them are the same as well. And so I can make a pretty strong argument that this triangle is congruent to this triangle, which means that this and this must be the same. So both of these are going to be 1/2 y, or the whole thing is y. 1/2 y. Now, in order to find the area of this rectangle, I'm going to need this height. I mean, I could try and use one of those methods that we learned in trig, like Heron's formula, which said, hey, if you've got the 3 sides, we can find the area. But I don't think very many of you remember Heron's formula. And the same goes with 1/2 AB sine C. We don't know that angle, and so I can't find that one. But yeah, I could probably do Heron's formula here. But I think instead what I'm going to do is say, okay, y is equal to 12 minus 2x. So when I look at this triangle, this is 12 minus 2x, and this is x, and this is x. And here, since this is half of y, this must be 6 minus x here. So now I do feel like I can use the Pythagorean theorem and say h squared plus 6 minus x squared equals x squared. And we'd like to solve this equation for h, but I'm going to have to FOIL here first. So let's do the foiling. No, I haven't fallen asleep. I'm just making sure that the recording is going. Yay, the recording is going. Okay. H squared plus 36 minus 12x plus x squared equals x squared. So I'm going to have h squared equals 12x minus 36. And that doesn't seem to help me very well, though I can do that. So that's my h. And in other lifetimes, I might celebrate at what good news that is. But in this lifetime, despite it being the magical year 2020, with all its plagues and disasters, I'm pretty much feeling like, yeah, I'm a happy camper that I only have to deal with that. And why did I want to find that? Because, well, the area formula for a triangle that I seem to remember is 1/2 base times height. So my height is this, my base is that. And we've got 1/2. So 1/2, 12 minus 2x times square root of 12x minus 36. I can always distribute that 1/2, and I get the area is 6 minus x times 12x minus 36 to the 1/2. And guess what? Now I'm ready to start the calculus part. So let's take a look at doing the calculus part here. So product, because these are being multiplied together, the derivative of this is going to be negative 1 times 12x minus 36 to the 1/2 plus the derivative of this 1/2 12x minus 36 to the negative 1/2 times the derivative of the inside, which is 12, times, oh, don't forget that, 6 minus x. Right? So we're doing the derivative of this times that plus the derivative of that times this. Okay, so let's do some factoring. I'm going to take out a 12x minus 36 raised to the negative 1/2. And here I'm going to be left with negative 1 times 12x minus 36 to the first. And then here, I got 1/2 times 12, that's going to be 6, so plus 6. I took out all of that, times 6 minus x. Okay, so that's what's left over. And if I tidy up the stuff here, minus 12x plus 36 plus 36 minus 6x. And that's going to be 72 minus 18x. Okay. And then out here, we've got 12x minus 36 to the negative 1/2. So there's a prime. Now, this is when the derivative is undefined, right? See that negative exponent? That means that's in the denominator. So I know this function is undefined when x equals 3. Or I know that the derivative is undefined when x equals 3. And here, ooh, I get 72 minus 18x equals 0. Which means 18x equals 72, or x equals 4. So we're looking for the maximum area, and I'm going to take my little tidied up A prime, and I'm going to make a little tidied up A prime sign chart. We've got 3 and 4. Yeah, 3 and 4. And remember, these are x values. So if I try a number to the left of 3 in A prime, like 0, that goes away, and that goes away. Wait, look at that. I got 1 over the square root of negative 36. Yeah, we don't exist over here. There's nothing over there. Well, that helps me understand this a little better. And then what about 3.5? Well, 3.5. I know the denominator is going to have to be positive. Well, I know that this is 3 times 12, and this is 3.5 times 12, so this is going to be a positive number in here. So I've got a positive on the bottom. On the top is what I'm interested in. I've got 3.5 times 18. So those are going to cancel, and I'm going to get 63. 72 minus 63, that's positive on top, positive on the bottom, and I end up with positive. But if I put in something bigger than 4, like 5, I'm going to have, yes, still here a positive, because 60 minus 36 is 24, and I can take the square root of 24. That's going to be positive. If I plug in a 5 here, I'm going to have 90. 72 minus 90 is definitely a negative number. Negative divided by positive is negative. And we see our max is occurring when x equals 4. And what are we asked to find here? Find the lengths of the sides. Well, remember in our picture that we said this was x, x, and y. And we said that y was equal to 12 minus 2x's. Since we know that x equals 4 is our max, we're going to do 12 minus 2 times 4. Oh my goodness. So what shape is it that maximizes area? It's the equilateral triangle. Hi, little equilateral triangle. I didn't know you had that special quality, but it's true. So the area of the it is that hour. Isosceles triangle is maximized when x equals y equals 4. Do we need anything besides find the lengths of the sides? Because to the left of x equals 4, a prime is greater than 0, and to the right of x equals 4, a prime is less than 0. All right, there's number 6. Let's take a look at 7. Find the dimensions that can be inscribed in a circle with a radius of 10. Ooh. So, at a circle, I'm going to choose the origin to be the center of my circle. We're told that the dimensions are inscribed in a circle with radius of 10. We know that radius is 10. But we're talking about a rectangle. Let's imagine the circle comes to that point. We can call that point xy. So I know that this distance is y, and this distance is negative y. So that whole side length, y minus a minus y, is 2y. I know that this distance is x, and this distance would be negative x. And so x minus a minus x is going to be 2x. So when I think about the area of this rectangle, I'm thinking that area is 2x times 2y, where area equals 4xy. Do I have a helping equation? Oh, I wish I had a helping equation so I could rewrite area in terms of one variable. And curiously enough, I do. I know that this is a circle whose center is the origin and whose radius is 10. So I could write this 10 squared. Now, this is my helping equation. X squared plus y squared equals 100. Y squared equals 100 minus x squared. And y equals square root of 100 minus x squared. Okay, and yes, we can do the plus or minus. However, I'm not going to do the minus, because really the minus is going to get me the same solution because I'm going in the opposite direction. I'm just going to say that this whole thing is 2y. So 2 of these. And is that what I need? No, all I need is 4x square root 100 minus x squared. Okay, so that algebra all being done, I now need to take my derivative. So let's see. A prime, its product rule, right? Multiplication is 4 times 100 minus x squared to the 1/2 plus 4x times 1/2 100 minus x squared to the minus 1/2. Don't forget to take the derivative of the inside, negative 2x. Okay, so we can take the smallest power out. And that's going to be a prime equals 100 minus x squared to the minus 1/2. What's left over? Well, this 4. We subtracted a minus 1/2, so we're going to have a positive 1 here. 100 minus x squared to the 1 plus, well, that 1/2 and that 4 are going to make 2 times 4 times negative times x squared. So I'm going to have minus 4x squared. Okay, I can tidy up in here and have 400 minus 4x squared minus 4x squared is minus 8x squared. And here we have 100 minus x squared to the minus 1/2. So when is a prime undefined? When this is equal to 0. When is a prime equal to 0? When this is equal to 0. So I'm just going to set each of these factors equal to 0, and I'm going to get x equals 10 here, and here I'm going to have x equals square root of 50 or 5 root 2. And yes, I could have the plus and minus, but again, I'm going to build this going in the positive direction only, and certainly we could make the suggestion that what kind of rectangle are you talking about that has a side length that's negative? It doesn't make a lot of sense to me, which is really why I'm keeping this positive. Okay, so we've got some values, and it may be helpful for us to go back to this area formula and say, does this have a restricted domain? What's the smallest by x can be? Well, 0. And we've got 5 root 2. If root 2, this is 5 times 2, and this is less than 2. So 5 root 2 goes here, and 10 goes here. And yes, 10 is the endpoint, because 100 minus 10 squared, that's going to be 0. So I get an area of 0 when x equals 10. So here are my values, and I want to try them out in y prime. If I plug in a 9, so 81, 100 minus 81, that's positive. 81 times 8. 81 times 8, well, isn't that it's going to be 648? That's definitely bigger than 400. So when I plug in a 9, I get a negative times a positive, which is a negative. If I plug in a 1, I've got square root of 99, that's definitely positive. If I plug in a 1, 400 minus 8 is positive, positive times positive is positive. So I can see that my area is going to be a maximum when x equals 5 root 2. And we want to know the dimensions of this rectangle that has the greatest area. So in addition to knowing that x equals 5 root 2, we need to know what y is. So didn't we have a helping equation? Didn't we know what y was equal to? Yeah, we said that y was the equation of the circle. 100 minus x squared. So that's my y value. If I square this, I get root 2 times root 2 is 2. 5 squared is 25. 25 times 2 is 50. So that's going to be square root of 50. Hey, isn't that square root of 50 also? Isn't that interesting? So when y equals 5 root 2 and x equals 5 root 2, the dimensions are maximized. The area is maximized. But let's look at what they said. They said, find the dimensions of the rectangle. And remember, when we drew this rectangle, this was 2x, and this was 2y. So my dimensions are actually 10 root 2 by 10 root 2. Not these. What I found here is simply that this is 5 root 2, and this is 5 root 2. But we know the dimensions of the rectangle are 2 of those distances and 2 of those distances, which is why these are my dimensions. So I might say dimensions of the rectangle with max area inscribed, maybe you don't need to do this part of the sentence. Inscribed in a circle whose radius is 10 are 10 root 2 by 10 root 2, and then our justification, because to the left of x equals 10, no, I checked 5 root 2, a prime was greater than 0, and to the right of x equals 5 root 2, a prime is less than 0. Okay, and so notice how many sentences? Well, it's really just one. Now, while Ms. Allen will say, don't you write that as one sentence? And she's probably right for that. I'm going to write it as one sentence because that one sentence contains all the information I need. It's got the dimensions of the rectangle. It tells me the situation, and it justifies the situation as well. I'll still love you if you turn this into 3 sentences, but I'm still going to write my one sentence wonder there. Okay, so number 8. Number 8 says, express the number 4 as the sum of two positive numbers. 4 equals x plus y, the sum of two positive numbers. So x has to be greater than 0 and y has to be greater than 0. In such a way that the sum of the cube of the first number plus the square of the second number is as small as possible. So sum. Yeah, see how it's not equal to a number? See how it's equal to a number? Helping equation, the one you want to take the derivative of. Okay, I'm just going to go back and check, because look, it says maybe you should go back and read this a couple of times to make sure you know what's being asked here. I love that advice, because I was just about to do that again. So we've got the number 4 as the sum of two positive numbers in such a way that the sum is the cube of the first number and the square of the second number, and we want as small as possible. Well, again, I'm going to need to take the derivative of this and set the derivative equal to 0. I want to be considering my endpoints, and I really want this sum formula to be in terms of one variable. So luckily, I can say that y equals 4 minus x. So I come over here and I can write the sum as a function of x to the third plus 4 minus x squared. And you know what you may find easy is to FOIL this out, and then you'll have this big polynomial, and you just use the power rule. But I'm going to go ahead with using the chain rule here, because I know that I'll only get more scared if I avoid the chain rule more. Don't forget to come and take the derivative of that inside, which is negative 1. Okay, so we've got 3x squared, negative times positive is minus 8, negative times negative is plus 2x. And so we've got 3x squared plus 2x minus 8 is s prime. Does this quadratic trinomial factor? Well, let's see, 3x, x, 2, and 4, and this is going to be a plus and a minus. I think that works. There's minus 8, negative 4 plus 6, positive 2, and there's my 3x squared. Nice. So there's s prime. I know that s prime equals 0 at x equals negative 2 and x equals 4 thirds. Really, you should probably set this equal to 0 and add the 4 and divide by 3, because I have a lot of students in calculus who don't write 4 thirds here, they write 3/4 here. And the way to not write 3/4 here is to actually show that step. I understand it takes a few seconds, you'll never have them back, but you're not going to have that risk of doing some sort of inversion there. So here's what I notice. X has to be a positive number. So this, sorry, Also, I've got some boundaries. X has to be bigger than 0, but can x be bigger than 4? Well, only if y is negative, but here we're told y has to be positive. So I think I've got some boundaries here for my s prime sign chart. And that's 0 to 4, and one critical number on that interval at 4/3. So if I come down here to s prime and I plug in a test value of 1, I'm going to have 3 plus 2 is 5 minus 8 is negative. And if I plug in a number bigger than 4/3, like 2, I'm going to say 6 minus 4 is 2, 2 plus 2 is 4, and so 2 times 4, that's positive. And so I do get a minimum when x equals 4/3. So what am I supposed to do? Express the number 4 in such a way so that it doesn't actually say find the numbers, but it's supposed to say find the numbers. So if I know that one of the numbers is 4/3, and weren't you expecting, a whole number value here? It turns out no, I wasn't expecting. If I plug in 4/3 here, so I can find y, I'm going to have 4 minus 4/3, which is 12/3 minus 4/3, and I get 8/3. So those two numbers are 4/3 and 8/3. And yeah, I do want to write a justification here. And my justification is going to say that the sum is minimized when x equals 4/3 and y equals 8/3, because to the left of x equals 4/3, s prime is less than 0, and to the right of x equals 4/3, s prime is greater than 0. All right, that was problem number 8, and yes, I got that one correct. It's very nice to have the answers. I like checking. Number 9. But find the coordinates on the curve x squared minus y squared equals 16. And this is a hyperbola, which is nearest, i.e. the shortest distance to the point 0, 6. Write the function in terms of y's, not x's, in order to find happiness. Oh. Okay, so what is it that we're doing? We're saying distance formula. Distance formula is x minus x of 1 squared plus y minus y of 1 squared. Here's our distance formula. Often our textbook says, why don't you just do this one? And then not have to worry about the Pythagorean theorem. Okay? This goes here, 0, so minus 0, and here we have 6. So x minus 0, yeah, that's just x squared there, huh? Oh, I see why that. Look, x squared is equal to 16 plus y squared. Oh, so I can get rid of this and replace it with that. So 16 plus y. Is that, did I? No. Come on, Mr. Don't be a rude. Okay, so we know that x squared, this is x minus 0 squared. We know that x squared is 16 plus y squared. And so now I have that distance in terms of y stuff. I know that many of you are going to feel more comfortable doing it this way instead of using the d squared. I'll happily do it this way. So over here, I'm going to have dy dd. And over here, I'm going to have it in half. 16 plus y squared plus, FOIL this out, y squared minus 12y plus 36 to the negative 1/2. And now we want times the derivative of the inside. Derivative of that is 0. The derivative of that is 2y plus the derivative here is going to be bring down 2 And then finally, the derivative of the inside is 1. So I can combine like terms here. 2y squared minus 6y plus 36. And that's all under a radical in the denominator with that 1/2. Ooh. Okay, so let's come back up here, give ourselves some more space, and say that 1 over 2 square root 2y squared minus 6y plus 6 times this thing over here, which is 4y minus 12. And there's our dy dd. So, no, dy. Thanks. Dependent variable out in front, independent variable y on the bottom. Always, always, always. Okay, so what do we know? Well, here's our derivative, and I'm going to set each piece equal to 0. This tells me when the derivative is undefined, and this tells me when the derivative is 0. So I'm going to get y equals 3 for the derivative d prime equals 0. But what about this? Does this factor? What a great question. I'm going to take a 2 out everywhere. Oh yeah, well, no, wait. No. Come on. It's tempting, but it would only work if this were negative. The factors of positive 18 are either both positive or both negative. And since this is minus, then those numbers have to be both negative. And so negative 6 and negative 3 is going to be negative 9, not negative 3. If this had been a minus, then I could do something like that, and then yes, this would factor. But this does not factor. That is a positive. So, here's a way to put yourself at ease. This is a parabola. You know that the vertex of the parabola is at minus b over 2a. Minus a minus 3 over 2 times 1. So I get 1/2 is where my vertex is. So if I plug in 1/2 here, what do I get? Well, let's see. If I plug in 1/2, I'm going to have 2/2 squared minus 3 times 3/2 plus 18. And yes, I know there's a 2 outside. But what I'm going to do here is show that this input value for the vertex gives me a vertex whose value is positive, meaning that this graph doesn't have any x-intercepts, but y-intercepts in this case, and therefore the derivative is never undefined, and we only have the one critical value. But let's just confirm it. This is 9/4 minus 9/2 plus 18. So let's make a common denominator, and that's going to be 9/2 minus 9/4 minus 18/4 plus 72/4. And look what happens. We've got 81/4 minus 18/4. That's definitely positive. And so this vertex of this upturned parabola occurs at 3/2 and some positive number. Therefore, this parabola, the one down here, is never equal to 0, and therefore this derivative is never undefined. So I'm looking at this critical value, d prime of 3. Now, let's test something on either side of it. Points on the curve, minimize distance, shortest distance to the point. Shortest distance to the point 0.6. Okay, so if I try 0 and try 4, put in zeros here, I'm going to have positive over positive, all that's positive. If I plug in a 0 here, I got negative. Negative times positive is negative. If I plug in a 4, 16 minus 12, that's positive. This is still positive. Positive times positive is positive. So were we looking for a min? We wanted the shortest distance. And so the shortest distance And you might want to be explicit here about what shortest distance, the shortest distance between this curve and this point occurs when y equals 3, because to the left of y equals 3, d prime is less than 0, and to the right of x, now y equals 3, d prime is greater than 0. All right, and but we need to find the where, don't we? So I'm going to have to take this y value and plug in here to find x. So let's not forget to do that. We plug in a y equals 3, we have x squared minus 9 equals 16, or x squared equals 25. And when we take the square root, plus or minus 5. So we've actually got two ordered pairs here. One is negative 5, 3, and one is positive 5, 3. Okay, and just like we do with, say, a circle or an ellipse, this hyperbola is going to have two places that are the same distance away from this ordered pair, 0, 6. And that's a string mark. And these are those 2 points. Don't forget to write the, oh no, we did write the justification. Yeah, so there we go. These are our ordered pairs where that happens. And my advice on the worksheet was spot on. I definitely wanted to be writing everything in terms of y's, not x's. And you might want that, but no, I don't want to go there. Okay, we've got a square piece of cardboard. Oh my gosh, we've seen this problem so many times since pre-cal. I hope it becomes familiar with you. I definitely have had students who, even though we did this problem 4 times in pre-cal, and again a couple times here in calc, that they still aren't comfortable with this. And so really I suspect that you might want to, if that's you, you might want to spend a little more time owning the material as opposed to merely acknowledging and bowing to the material. So I'm going to fold up the flaps, and I'm going to get this open-topped box. It is open-topped box. These are the same size. And so we can say this is 12 minus 2x, right? Because here's 12, and here's an x, and 12 minus this will get me this piece here. I do the same thing over here and say that this part of the box is 12 minus x, or 12 minus 2x, and here's an x. So my volume is going to be x times 12 minus 2x squared. Okay, and what are we looking for? What size squares should be cut to obtain the largest possible volume? Okay, so yeah, you could FOIL this and then distribute, but really I think I can do product rule faster. So I'm going to go with product rule. So the derivative of this times that, plus that times the derivative of this, which is going to be 2. Leave the inside alone. Don't forget to subtract 1, and don't forget to come back and take the derivative here, minus 2. So what do we have about v prime? Well, I can factor a 12 minus 2x out, and I'm left with that 1 and one of these, so 12 minus 2x. Now my plus sign, I've got 2 times negative 2, which is negative 4, times x, that's going to be minus 4x. And this is what I factored out. So I can just tidy this up as 12 minus 6x times 12 minus 2x. And there's v prime. So it looks to me like I've got a critical number at 6 and a critical number at 2. So if I were to make a v prime sign chart, actually not a graph, a v prime sign chart with 2 and 6 on it, I might also think to put 0, because the smallest x can be is 0, right? I can't have negative, I can't cut a negative side length out. So I'm going to test 1, I'm going to test 3, and I'm going to test 10. Let's see what happens. Okay, so if I plug in a 1 here, I get 12 minus 2 and 12 minus 6. Positive times positive is positive. If I plug in a 3, I've got 6. 12 minus 6 is positive. 3. 12 minus 18 is negative. Negative times positive is negative. And then over here with 10, well, 10. Yeah. So if I plug in a 10 here, I have 12 minus 20, that's a negative. And 12 minus 60, that's a negative. And negative times a negative is a positive. I do get a minimum here. We were asked for the maximum. That occurs at 2. Also remember, when we did this problem, back in pre-cal especially, we've got 2, and we've got 6, and what do we? No, we don't. We have zeros at 0 and at 6, and 6 has a bounce. This is negative 2x to the third, so it must be coming. Well, that doesn't feel right. Oh, when I squared that, that's positive and positive. Okay, sorry, I had to do some thinking there. And don't forget the bounce at 6. So here, we do get a minimum. We do see that horizontal tangent on this V graph. But what about past that? That's a positive volume. But what we said in class when we talked about this was that if I put something like 10 in for x, how can I cut 10 off this side and 10 off this side if the whole thing is only 12 long? I need the whole thing to be at least 20 long in order to cut 10 and 10. So this doesn't exist, and this doesn't exist. No negative x values either. Our domain is simply 0 to 6, and we seem to have found out that at x equals 2, we have our maximum occurring. Okay? And lo and behold, that's what we have as our answer in number 10, and I'll let you write the justification sentence for that. Okay, well, there's that worksheet. I look forward to seeing you in the next.